Other speakers join, let me start. Being the convener of the session, I take this opportunity to start now. Meanwhile, the other speakers will join us. So it's a great event. Thanks the organizers for giving the opportunity to me to convene this session. And it's a very important session while we speak about the nutrition of drylands, nutrition and management of drylands, and nutrition not only of the drylands, but the populations of drylands also. So as we know, drylands are one of the greatest environmental challenges of our times, and climate change is making it worse. Drylands, with a home of approximately 2.7 billion people, occupy around 38% of the land on the earth, covering much of the North and Southern Africa, Western North America, Australia, the Middle East, and Central Asia. Approximately 90% of the dryland population live in the developing countries. So basically, the major causes and processes, if we look at the world's water scarce regions, have degraded due to a cumulative impact of climate variations, land mismanagement, and unsustainable freshwater use. This has left their soils unsupportive for crop production, livestock, and biodiversity. A scarce and unpredictable rainfall causes susceptibility to land degradation and poor soil fertility in drylands. Now, a loss of soil fertility could be through a loss of nutrients such as nitrogen, phosphorus, and potassium, or a decline in the amount of organic matter in the soil. In arid, semi-arid, and dry subhumid regions, the soils also suffer from salinity and alkalinity. A low and imbalanced use of fertilizers in drylands keeps the productivity very low. Due to scarce water availability, mostly single season cropping is practiced, and the land is left fallow for half of the year. Low soil moisture, erosion, leaching, and extreme weather events lead to high nutrient losses from the soils. And organic carbon, the deficiency of secondary and micronutrients such as sulfur, zinc, and boron further limits the potential of drylands to produce higher yields. So there are some solutions being worked out by various researchers. Both water and fertilizer use efficiencies need to be enhanced, which ensure the appropriate uptake of nutrients by the plants. The availability of good quality water in the root zone at critical stages is very necessary. In saline and sodic soils, use of good quality irrigation water and subsurface drainage has been helpful in enhancing the soil qualities. However, an integrated community-based approach has been observed to be successful in improving the productivity of these lands and uplifting the economic status of these resource-poor farmers. Conservation agriculture, including resources, conserving technologies, regenerative agriculture, foliar nutrition, soil amendments like biochar, gypsum, other sulfur-based amendments, balanced use of fertilizers, biomass composting, crop rotations, including legume, integrated nutrient management, etc., have proved promising for mitigating the climate change effects in highly vulnerable drylands. Climate smart technologies, including climate information services, promoting stress-tolerant crop varieties, crop insurance, use of satellite images, application of artificial intelligence and machine learning, etc., are the need of the hour. Today's session includes 5 research papers on nutrition in drylands and their management, which have demonstrated the role of technology in ameliorating degraded lands. fertilizer management, irrigation water quality, and moisture stress management in arid and semi-arid regions of different countries. You would see how these researches are helpful in improving soil conditions, enhancing crop yields, and economic status of the farmers. So with this, I introduce you uh, to the speakers, our speakers of today's session. One is Professor Dr. A.N. Singh from India, who will be presenting his experience on a large project on reclamation of Sodic lands in arid and semi-arid environments of India. Professor Yuri Miyahu from Israel, Professor Ran Irel, and Dr. Amanullah from Pakistan, whose work is on foliar application of nutrients. Dr. R.P. Dheer. Dr. R.P. Dheer and Dr. Amanullah have not received yet the email notifications to log in. So meanwhile, I would request Dr. Singh to present his work, his talk. Meanwhile, we try to connect to Dr. R.P. Dheer and Dr. Amanullah. So will you be able to share the screen, Dr. Singh? And Dr. Amanullah. So will you be able to share the screen, Dr. Singh?
Host has disabled screen sharing.
Screen sharing is disabled by the host.
Dr. Verma, you are also co-host, then you can please do it.
Yeah. Okay. So I'll share the presentation, no problem.
No, you enabled this share screen option.
Yeah.
It is disabled. Please enable it so that speaker can share their screens.
Okay, fine. So just see if you could.
Enable this share screen option. It is disabled. Please enable it so that speaker can share their screens.
Okay, fine. Just see.
Now you can share your screens. It's now ready for. Now you can share your screens. It's now ready for.
Yes. Should I start?
Sir.
Yeah, please bring it on presentation mode.
Okay, yeah.
Please start slideshow.
Yeah.
Slideshow.
Yeah.
Please bring it on presentation mode.
Yeah.
Start slideshow. First one, sir, from beginning.
Yeah.
Yes.
Yeah.
Right.
Thank you, Dr. Dharmesh, for introducing me to
First one, sir, from beginning.
yes. Now, thank you, Dr. Dharmesh. The topic of my talk is on the reclamation of saline and sodic lands in India. The land degradation, no, there is echo. Already there is echo. I think there is a great confusion.
इंटरनेट की वजह से हो रहा है शायद दूसरी जगह पे इतना अच्छा
Audible? Hello? Am I
audible, sir, please?
Okay.
Yes, sir, you are audible, sir, please.
Okay. Now, the land degradation and saline sodic lands reclamation that has been carried out
Audible, sir, please.
in India.
Yes, sir, you are audible, sir, please.
Yeah.
इको हो रही है क्योंकि आप बोलिए
There is an echo, so the problem is because of that. About 57% of the land area in India is degraded, and soil salinity and sodicity affected land are 6.7 million hectares. Large-scale land reclamation work has been carried out in India in different states, mainly Punjab, Haryana, Rajasthan, Uttar Pradesh, and Bihar. In Uttar Pradesh, we have reclaimed about 0.4 million hectare area between 1993 to 2018 in 3 phases under UP Sodic Land Reclamation Project. Extensive use of geoinformation technologies has been made in project planning, implementation, and monitoring. In this presentation, I will describe how the geoinformation technologies have been used in mapping and in implementation, preparation of implementation plan by the Land Reclamation Agency, and post-reclamation monitoring of soil quality, groundwater, land use change, and project sustainability. Now the background of sodic soils. Soils have excess of sodium in the soil complex, which is detrimental to plant growth and impairs its physical condition. The biological activity is reduced due to high pH, which goes up to 11, and ESP up to 90. Soluble salts in these soils contain sodium carbonate and bicarbonate, which saturates the absorbing complex with sodium. Then steady supply of alkali by hydrolysis and leads to carbonates and bicarbonates precipitation at high pH and causes subsoil sodicity. And this problem is there in arid and semi-arid climates because of over-irrigation, and the land may completely go out of cultivation or may produce much lesser than its capacity. This map shows the extent of sodic lands in purple color. You can see the patches, sodic lands in different districts of the state located mainly in the central part. Now, in the three phases, extending from 1994 to 2017, 400,000 hectare land has been reclaimed. This PPT shows the beneficiaries' share extends from 12 to 25%. The project costs. About 29 districts have been covered. More than 240,000, more than 800,000 beneficiary farmers were involved in the entire project. Now, the requirement for the execution of reclamation project are as follows. We have to locate the Sodic lands with the plot numbers on the village map and then categorize these lands into different categories. And the categories that we have made in are A, B, and C. The A Sodic lands are the ones which are cropped but productivity is below normal. Class B lands are the single cropped areas and pH ranges from 9 to 9.5, and Class C lands are barren lands where pH is more than 9.5 and there is excess of sodium, because of which the exchangeable complex of the soil is saturated with, highly saturated with sodium. Then we need to know the area under Sodic lands, each class, and we need to know the soil characteristics of each class in terms of its pH, EC, and gypsum requirement. We have used a multi-stage remote sensing approach in the selection of reclamation sites in the district and villages, and we used initially a small scale map, 1:50,000 scale, to select larger patches where the reclamation is to be started. Then we used 1:50,000, 15,000 scale aerial photographs for mapping of each village, which are to be taken up for reclamation initially, and subsequently we used the high resolution satellite images for mapping at the village level. The reclamation sites within the district were selected based on the criteria of sodicity, the presence of linked drains nearby, and the groundwater acceptable for irrigation. Now the main component the project included the selection of sites, on-farm development, which included provision of field and link drains, addition of gypsum, and irrigation development using shallow tube wells for one tube well for each 4 hectare area. Then rehabilitation and maintenance of main drains were an important component of the project. The reclamation technologies are dissemination support for the establishment of tree crops on privately owned land, and forestry species on community lands were also tried. Institutional capacity building of the institutions involved in the project was also an important component. Environmental monitoring which included monitoring of soils, water, land use, and biodiversity. Pre and post reclamation was also an important component. This map shows the presence of different types of sodic lands marked as A, B, and C. The C sodic lands are the barren lands. B sodic lands are the single crop where paddy or rice is grown, but there is no crop during the winter season. And A are the lands where we have both rice and wheat being grown, but the growth of wheat is very poor. Soil environmental issues monitoring component involved soil sample to be collected annually after winter crop. It continued for 5 years and up to 120 centimeter of soil profile. We monitored these areas continuously for 5 years, and we found improvement in the surface erosion, significant reduction in soil pH, and improvement in soil organic carbon. And these improvement in soil quality in surface horizon have created environment suitable for growing crops. Now this shows the areas that were used for soil monitoring. You can see pre-condition, pre-reclamation condition. There are few patches of cultivated lands shown as red color on the satellite image. And you can see in this part of the village the reclamation status, which is being shown by the red color on satellite images. GIS has been used in concurrent monitoring of ground and surface water in this project. The monitoring program was designed to understand the movement of salt and soil profile in the soil profile and into the groundwater system. Groundwater levels were collected from open wells, piezometers, tube wells, and also automatic water level recorders. Then we collected water samples post-monsoon season and analyzed for pH, AC, cations, and anions, and trace elements. Spatial variations in groundwater levels were compared using grid interpolation in different years. The area under shallow groundwater.
I apologize, but we have to end the meeting to end the lecture in 1 minute. If you can please conclude so we can continue to the next speaker.
The drainage improvement was another.
I apologize, but we have to end the meeting to end the lecture in 1 minute.
Yes.
If you can please conclude
please.
So we can continue to the next speaker.
Okay. There was post-reclamation land use change monitoring also that was carried out. And you can see here the pre-reclamation condition on the left and reclaimed areas on the right. And then the benefits of the project included about 800,000 families benefited. There was increase in productivity of cereals, increase in the cropping intensity from 45 to 206%, increase in crop income, and soil quality improvement, improvement in floral and faunal biodiversity, and then we also found that it took some time to build the capacity at level of different institutions. And once that was done, then the reclamation was made and it was quite successful. So in this presentation, I explain the use of information technology in the reclamation and land reclamation process in the Uttar Pradesh state of India, and monitored the post-reclamation status in terms of soil quality, land use changes, successes and failures of implementation to find out the sustainability of the project. And the periodic monitoring using remote sensing also helped us doing midway correction in the project. And a large saving in the project cost of GIS implementing agency at different stages also show that it helps in the decision making in the reclamation project. Thank you very much.
Thank you, Dr. Singh. Now, Dr. Dhir has also joined us, and I would request him to start his talk. We have already, we are running late, and would you be able to share the screen, or shall I do for you? Are you able to see the screen?
Yes, the screen is visible.
Okay,
yeah,
fine.
but my photo is not appearing. I don't
Yeah.
mind my photo, but let me, I don't want to upset your schedule further. We are already running late. Something has gone wrong somewhere, but our settings are the same.
Yeah, it is the thing which I finalized for you, Dr. Dhir.
Yeah, this is the same. Yeah.
Visible.
Oh, thank you, thank you,
Yeah,
thank you very much,
visible.
Dr. Verma. Yeah, please.
Yes, it is
I'm
visible.
speaking on Thar Desert, which is in the Indian subcontinent. Some part of it lies in Pakistan. A major part is in India, and that is what I will be speaking on. Thar Desert, next. Thar Desert is on the westernmost end of the mid-latitude deserts, and with a mean annual rainfall of 150 to 450 millimeter, that is monsoonal in character and marked by high inter-annual fluctuation. Therefore, droughts of various intensity are an inherent feature of the climate. Next. Yeah. The region is distinguished among the world arid zones also by its long history of human settlement and land use. A dense population, presently 130% per kilometer square, and of livestock. In terms of adult cattle units, 161. And besides, there is a high incidence of arable farming, 68%, which very few deserts have it. Such an incidence, high incidence of arable farming. And they have, the local people had evolved by their own experience several practices like mixed farming, agroforestry, mixed cropping as the features. In the past, cattle were the dominant species, let us say even 55 years, 60 years ago. But presently, the sheep and goat have increased vastly in numbers. and the cattle have come down. The camel also has come down. Next. Fears in early 1950s that condition within the Thar desert were not deteriorating, and further that the desert was advancing northwards to the prosperous area of India. The then government launched a program to develop a technical know-how and also undertake some development effort in areas of greening of the desert, sand dune stabilization, and pasture land regeneration. And a few years later, the dry farming and several other spheres of research, as well as that of natural sources survey and assessment, were added to this program. And I should say that Thar Desert is one of the best investigated area in terms of natural source survey. Next. And a huge amount of effort was made to develop local groundwater and divert some of the Himalayan river waters in the form of canal to the Thar Desert. Presently, 30%, about 30% of the grass area of Thar is under irrigation by one or the other source. The irrigated lands are increasingly cropped by cash crops like cotton, groundnut, condiments, mustard, and spices. And their economic contribution amounts to over 2/3 of the total produce of the region. The canal system is also taking care of the industry as well as drinking water requirements of the region. This has really done wonders, particularly in areas with drinking water, besides, of course, irrigation for agriculture purposes. Next one. And there has also been a very good success with bear. Several varieties of bear not present earlier were developed at Jodhpur, and these have been well adapted by the farmers in the region. In fact, the bear Ziziphus of Jodhpur find market right up to Delhi and beyond, and so also in the south. And recently, in the last 5-6 years, date palm cultivation as well as pomegranate cultivation in a high technology mode has been taken up on a sizable scale. These are really unique developments. Next. Yeah, the agronomic and various socio-economic programs, namely drought relief, poverty alleviation, rural employment and housing, and infrastructure development have brought in great improvement in living conditions. In fact, people's living conditions become in several areas incomparable to what was in the past. There have been so much development. Distant migration of population almost gone, though livestock migration to neighboring regions, particularly of sheep, continues. Thar has been a favored area for wind power and solar energy generation. Presently, Thar is having an installed capacity of 26,000 megawatt. Next. Summing up, though wind erosion is in the precious canal area has been controlled to a good extent, and Thar in general appears much greener than ever before. Yet wind erosion, particularly in the westernmost area, continues to be a serious problem. The situation of groundwater depletion, in fact, is the most serious, I consider. The majority of aquifers are showing a depletion of 1 to 2 meters per year. And I suspect then in the coming 5 and 7 years, the irrigated area from groundwater is going to come down despite our use of sprinklers and various other economical methods. Happily, wind regime in general in the area has slowed down in the past 3 decades. However, global warming is poised to adversely affect Thar in several ways. Most models predict a further increase in already existing variability in rainfall, and that will be killing because already we had a drought situation frequency, and over that, if there is a more addition to the erraticity, this is really going to badly hit arable farming. Studies predicted an annual temperature rise for Asia, which includes also our region, of 3 to 5 degrees centigrade in the coming decades. And for arid zone, it has severe consequences because it will greatly increase the aridity, and also the water requirements, crops and natural vegetation. The precious winter season crops will face a further shortening of growing period, lending to an estimated loss of yield by 10% and more. Thank you very much. Really, I am thankful for waiting, and my presentation is through. Thank you. Okay.
Thank you, Dr. Dheer. You presented your slides very timely. Now I request Professor Yuri Miyaho to present his presentation.
Can you see my presentation?
Yep.
Good afternoon from Israel, and today I want to talk about water. As a soil scientist, for many years we are looking what we have in the soil, take it into account when we are develop our fertilization management. And we didn't look after our water quality, and in the last few years we discovered that water should be considered when you are started or using nutrients. So I would like to share with you our experience in Israel. Israel established more than 70 years ago, and since then we are using fresh water for irrigation. Most of the country are under arid areas. So if we would like to have any intensive agriculture, we should have irrigation. So we use the fresh water, it's groundwater, surface water. This is very good water. But as a dry area, we don't have enough water. So sometimes in the 70s, we start to use brackish water. This water are groundwater we pump from the soil and use it for irrigation. We are still using this water in the desert, growing pepper, date palm. This water, including high level of chloride, is up to 5-6 decisiemens, and we develop a very nice management in order to grow intensive crop with brackish water. In the 80s, we start to take our water, the water from the cities, treat them, and use them for irrigation. This is recycled treated water. We have many names that we can use, terms for this water. The idea is to use this ugly water at the beginning, treat them, and irrigate. We have different pipes for this water. The color is purple, and this water is coming to be a major part. We must remember that it's effluent, including mostly water, but many much more components. Most of the components that you have here are something we want to avoid to apply to our soil, but we have nutrients and we have some trace elements in this component we would like to have. So I will concentrate on that one and not with the other. You can see here that from the last 40 years, the amount of effluent that using for agriculture, it's increasing. Actually today, almost 50% from our total irrigated water coming from effluent. Lately, which is just less than 50 years ago, we start to desalinated water from the Mediterranean. This water is mostly for drinking, but part of it are used for agriculture. And the technique that we are using is reverse osmosis. We are separate the salts from the water and now we have pure water. This is old technique, but now it's used, and we, as you can see, today, 80% or 65% from total drinking water come from desalinated water. So just lately we discovered that we have different water, and we need to decide if we are going to take this water into account when we develop the fertilizer management for different crops. Here you can see the desalinated water characterization, and you can see that we have much less electrical conductivity, much less chloride, much less sodium, calcium. It's we should have calcium, so calcium is a little bit less, no magnesium at all, and a little bit more boron. So we have different water, and we must look on this water and continue. I'm going to concentrate on two parts of a component that we have in water, essential element and harmful element. Also, we have another things that we need to think about them, but today I'm going to concentrate on these two only. And I would like to start with the elements. You can see here 12 micro and macro elements. We have a little bit more, but they are not the elements that we are used to apply or fertilizer. In the left side, you can see the micro elements, and molybdenum, copper, zinc, manganese, and iron. We don't have in any kind of water. So I take these elements off, and I would like to talk a little bit about boron. You can see here boron concentration in the fourth type of water, and this is the concentration of the boron in milligram per kilogram or ppm. Fresh water, we have something around 0.5. Desalinated water, this is something we decide. We have between 0.2 to 0.4, and effluent, it can be up to 1 ppm, and saline water can be more than that, up to 2 ppm. In the red line, you can see the range of boron that we would like to have in our soils. So if we have less than 0.1, this is deficiency. And of course, the fresh water, sometimes if the soil cannot supply boron, we need to add more boron. In the desalinated water, it's sufficient, while in the effluent and saline, the concentration of boron in the water can be toxic. And this is something we are worried about. This is some phenomena of toxic boron. We have few areas that the boron in the soil are very high, and you can see how toxic symptoms can look. And to summarize the boron, in general, the boron concentration in desalinated water in Israel is not problematical, but without leaching, boron can accumulate in the soil to be toxic level. So this is something we need to be worried about it and look during the year. And from the boron, I want to go to the micro elements, start with the nitrogen. Nitrogen is the most important element. And you can see here that in the different water, we have different level of nitrogen. The desalinated water, it's very, very low, almost zero. Fresh and saline water up to 20 ppm. This is the unorganic nitrogen, and the effluent, sometimes it's higher. And this amount of nitrogen sometimes need to be taken into account. This is just for example, in citrus. In the Negev area, we need to irrigate the citrus 750 millimeter, and if the concentration of the nitrogen is 20 ppm, so this amount of nitrogen contribute 60% of the total nitrogen that we use for fertilize the citrus. The same calculation for olive, we get the same number, it's 60%. And you know that if we have 60% from the water, we need just 40% to apply. We don't need to apply 100%. The effluent, we have many aspects when you are using effluent. And what I want to consider is just two aspects. It's the nutrition and salinity and contamination to the environment. We run a project in the desert of Israel for 8 years using effluent for irrigation. In the Mediterranean climate, the rain is in the winter time, 4 or 5 months a year. What you can see here, this is the soil salinity, in up to 120 centimeters in the end of the irrigation season, and you can see that this is the electrical conductivity up to 3 or 4 decisiemens per meter. In the end of the season, we have 400, 500 millimeter rain. All the elements, the soluble elements, are leached out from the road zone. It was experiment that we run with different soil type, effluent and fresh water, and both types are leached out. And when we make the calculation, we show that the chloride that leached out from the soil in the effluent treatment was much higher than the fresh water. This is the unit of fluoride in kilogram per hectare per year. And in one treatment that we take into account that the nitrogen that we have in the effluent, in this treatment, and we compare how much nitrate we leached out from the root zone. So from the fresh water, we leached close to 60 kilogram per hectare per year, where in the effluent, it was twice the amount. And if you take into account the nitrogen, you can eliminate less the water in the soil. And this is very nice example to show to the farmer that when you have something in your water, you must take it into account. In that case, it's just 20 ppm of nitrogen that we have in the effluent. When we are talking about nitrate, we must remember that nitrate compete with chloride, and you have different concentration of chloride in a different type of water, can be very low in the desalinated water up to very high concentration. And just for example, you can see the competition between the nitrogen and chloride. This is experiment pepper, and you can see that as much as the chloride in the patiole, it's increasing, nitrate in the patiole decrease. So when you have saline water, you need to know that you need to apply more nitrogen in order to supply the same nitrogen availability. I would like to continue with phosphorus, and in that case we have just phosphorus in the effluent, something between 5 to 10 ppm. If we're making the same calculation for the nitrogen, we arrive to 70% from the total phosphorus we can apply. It can be applied by effluent in citrus and 50% for olives. So again, if you have just 5 ppm phosphorus, major amount can come from the water. Potassium, very similar story. Citrus, if we're using just 20 ppm the effluent, we have also 60% from the annual potassium fertilization. With olive, it's 60% too. So you can see that NPK that coming from the effluent can be covering at least half of the total amount for in that case, for orange and olive. As chloride and nitrate, potassium and sodium are compete each other.
Professor Uri, I'm sorry to interrupt. Please finish it quickly. We are running out of time.
I'm almost done. So we have competition between potassium and sodium, very similar as we have with chloride and nitrate. You can see this competition. This is in citrus, and this is no phenomena. So again, if you're using saline water, this competition must take into account. Calcium, it's very interesting because we have enough calcium in our water, all kinds of water, but calcium is very important for fruit quality. So this is something we need to take into account, and also plant resistance. And in this case, calcium can be important. Magnesium, we have magnesium in our soil, but not in the salinated water. And magnesium, of course, it's microelement. And today, when we are using desalinated water, we must apply magnesium. Sulfur are very similar. This is just showing that calcium and magnesium has competition as the other. And I'm just finished with the sulfur. And you can see with sulfur that sometimes we have different kind of desalinated plant that have zero sulfur, and sulfur as microelement need to be taken into account, and you must apply sulfur. So I want to finish, and just to conclude, each type of water has a unique chemical composition, and it should be known by the farmers and take it into account. Essential elements require independent consideration regarding management of crop nutrient. And the last one that you just saw, that if we have a sodium chloride, we must irrigate it and take it into account in order to increase the yield and decrease the leaching factor, increasing water and nutrient use efficiency, and decrease environment damage. I would like to thank you for listening, and to my colleagues that was part from this work. Thank you very much.
Thank you so much, Dr. Uri. Now I would request Professor Ran Irel to start his presentation. Professor Ran Irel is there?
Yes, I'm here. I hope you can hear me.
Yeah, we are hearing you.
Trying
please
to share my
yeah.
presentation.
We hear you with no background noises.
You should tell me. I cannot hear myself. Well, I'm hearing myself without background noises. Okay, you see the presentation?
Yes.
Yeah, good.
Yes,
Okay.
yes.
So my talk is very much a continuation of Uri's presentation, which was much wider, and he described the effect of nutrients in general as related to the water source or the water quality. And I'm also studying plant nutrition in Gilat Research Center. And I have a lot of interest in phosphorus, and I would like to tell you the story of phosphorus in Israel, which I think is very unique, because in Israel, drip irrigation is the most widespread irrigation methods. Actually, most agrosystems are irrigated by drip irrigation, as Uri explained earlier. And we used a lot the recycled wastewater. Again, this is exactly what Uri described. So why phosphorus? I think among all nutrients, phosphorus has tendency to both extremes. In many agrosystems, mostly low input agrosystem, phosphorus is a major limiting factor. Soil absorbs phosphorus very strongly, either acidic soil, phosphorus is absorbed to metal oxide, or in alkaline soil, phosphorus tend to precipitate with calcium, like we have here around the Mediterranean, while in many other agrosystems, in modern agrosystems, phosphorus is very frequently over-fertilized because its mobility is so low, because its availability is low, we apply a lot of phosphorus, which has huge effect on the environment, negative impact. I mean. So phosphorus is very interesting. Well, I wanted to give you a clue about the size of Israel. So the map of the states is very popular now in the news. This is Israel, which is about 8% of the states of Wyoming. Okay, so it's just a tiny strip of land, but highly populated. And when we look at precipitation, although we are talking about relatively small area, we have very stiff gradient of precipitation from over 1,000 in the north to practically zero in the south. Half of Israel is actually a desert, below 200 millimeters of rain, while the potential evapotranspiration is 10 to 100 times higher than the precipitation. So irrigation is mandatory, and therefore it's no surprise that drip irrigation was developed not so far from where I'm sitting now, in the heart of the Negev. And as I said, today most farmers use this for irrigation. It has quite a lot of advantages. It provides the water, the right amount of water at the right place at the right time, because roots develop around the dripper. And what is most relevant for us, it enables fertigation. That means the application of fertilization with the irrigation system. And how is that related to phosphorus? So in this case, I illustrate how phosphorus distribute from a single dripper here. Phosphorus was applied with the water, and later we mapped where the phosphorus is located. So after a single application, we see most phosphorus in concentration just around the dripper, about 2 centimeters from the dripper, while after about 6 centimeters, we couldn't find any more phosphorus. So again, we see that the distribution of phosphorus the mobility, so is very, very low, and the availability decreases with time. So this is 1 day after application. 5 days after application, we see the availability decreases due to precipitation and reactions with the soil particles. So while the phosphorus is absorbed in the topsoil, we see that roots tend to go further down, below these 5-6 centimeters. And so we have a condition where roots and phosphorus do not meet, because the upper layer, it tends to be too dry or fluctuate between very dry and very wet, between irrigations. And we have a problem. Phosphorus is in the upper layer, roots goes further down to moist area. And in very nice experiment by Alon Bengal from Gilat as well, he showed that if you apply phosphorus at low frequency, it does tend to accumulate in the topsoil, as you can see in the left panel. While if phosphorus is being applied at very high frequency, as high frequency fertigation, we see that the mobility increases significantly. And in this case, of course, the phosphorus will travel down and meet the active root zone. And we can see that also using plants. If we apply the phosphorus before germination, we see that the biomass is significantly lower than phosphorus that was applied soon after germination. So to summarize, fertigation enables both increase in mobility and increase in availability of phosphorus. So you can, the plant can meet the phosphorus when and where it needed most. So Uri already showed these slides that in Israel in the past 4 centuries, the utilization of recycled wastewater is increased significantly, and this has negative and positive sides. For example, very nice survey of Eran Rave and Alon Bengal from Gilat as well, showing that there is a continuous increase in leaf chloride concentration in citrus all around Israel due to the introduction of recycled wastewaters. That's the negative side, but what about the positive side? We tested it on olive that were irrigated either with fresh water or recycled wastewater. And you can see here the concentration of phosphorus in the recycled wastewater, which fluctuate greatly from 12 to 2, okay, an average of about 5. And this is very much dependent if it's winter time, so it tends to be lower. In the summer, it tends to be higher. What people are throwing to the waste, but we can see considerable amount. And when we summarize the average annual application of phosphorus, we see it goes as high as 26 kilogram per hectare on average for 8 years. So if the offtake by the fruit is about 5 kilogram per hectare, that's a considerable amount of in the soil. We see that the treated wastewater treatment accumulated phosphorus in the upper soil layer between 0 to 30 centimeter, no effect on deeper layer. And we see that also the plants, in this case, 2 varieties of olives, accumulate in the leaves more phosphorus. And what they do to the yield. So if we consider each individual year, differences are minor, but when we combine 8 years together, we see a significant increase in yield in the recycled wastewater, in spite of the salinity and all the other problems it delivers. So when we're looking at utilization of wastewater, we see that it contains quite a lot of phosphorus, and it should be taken into account. And in the specific case of olives that were not supplied with phosphorus, so we see a significant increase in yield in spite of the negative aspects. And the last aspect of phosphorus management is the utilization of organic waste. It could be either manure or compost or so on. You can see here that different sources of organic waste has different concentration of phosphorus. The municipal waste compost to 1.5 in wastewater treatment plant sludge, which is very high. When you multiply it by the rate of application, that can deliver most, if not all, of the phosphorus required for plants. And these are all recycled phosphorus, okay? The phosphorus in the treated wastewater, the phosphorus in the manure can supply most of the phosphorus required by plants. And that's combined with fertigation to enhance the availability. That's the main message today. Frequent fertigation, supply of phosphorus at the time it requires, to the place it requires, utilization of treated wastewater when we consider the phosphorus in it can meet the plant requirement. And in this case, we found that in the case of olives, the requirements were underestimated, and the utilization of organic waste also supply considerable amount of nutrients. And that's it. I hope I did meet the 15 minutes.
I think Professor Ranaril, thank you very much for a very interesting presentation, and very timely you have finished your presentation. And it's really interesting. We have heard about nitrogen. Much of people have been working on nitrogen, but phosphorus this presentation, of course, has been very interesting. So now our next speaker and the last one is Dr. Amanullah from Pakistan. His presentation is on foliar application of nutrients for improving the yield. Please, Dr. Amanullah, please.
Dr. Amanullah, please unmute yourself. Please unmute.
Okay.
Yeah,
So,
now it's fine.
Okay. The title of my presentation is a integrated foliar nutrients application improve cereal growth in productivity under moisture stress condition in semi-arid climates. Here, due to water stress or drought condition, we have a lot of problems. There is a water problem. Water is not available, and the death of animals, fisheries, and also if we look to the crops. So under dryland condition, water stress condition, we have these problems. Water stress in the drylands having not only water security problem, but also food security. You look to the picture, so it is clear that dryland, we have a lot of problems. The major problems here in the drylands are the climatic factors. This means that there is insufficient and unpredictable rainfall. And we have high temperature and high evaporation. This means the water is not available. We have a lot of soil problems. I will discuss this in the next slide. And we have socio-economic factors. For example, we have the yield is very low. So this low yield is the cause of the food security, here. And we have a technological problem in the drylands. For example, there is a lack of modern agriculture practices. The farmers and growers are very poor. They are not able to buy the seeds, fertilizer, pesticides, and herbicides. So this is a big challenge in the drylands here in our country. In the drylands, the soil fertility, so the soils here are not good. There is a native soil fertility status. There is low nutrients, low organic matter, imbalance or no fertilizer application, low rate of fertilizer application, poor fertility management, improper residue management. We have soil erosion problems, and climate change, aridity, having high, low rainfall in high temperature. So this our decrease in fertile land due to the uneconomic distribution. We have also uneconomic land policy. So I think foliar nutrition in dry lands for cereal crops is important here, because a foliar feeding is recommended when environmental conditions are not good. For example, in drought condition, temperature, high temperature, insects, pest attacks. Foliar spraying is a very efficient method. A plant can absorb nutrients through leaf quicker than roots. So uptake of various plant nutrients ranges from, it is 900 to 900% faster as compared to the roots under when there is problem in the soil. Plants are able to absorb the nutrients through stomata in epidermis. If foliar nutrients are mixed with insecticide or fungicide, so this will reduce the cost of productions. Foliar feeding is favorable over soil application, and it is associated with high and better crop and fruit quality. The objectives of my students' research is to investigate the impact of soil and integrated application of foliar nutrients on wheat in mass productivity under water stress conditions. I will share some research. I will just share the mean values because the experiments are very large. There are two experiments on wheat crops. So experiment one is grain. I will just share you the grain yield response to foliar nutrition. So in the first experiment, grain yield response to zinc and boron application in their time with and without moisture stress condition. So if we look to the with stress conditions, So the yield is there is difference. For example, without stress condition, when we apply 1 or 2 irrigation, so the yield is higher, but under stress condition, the yield is less. But at boot stage, in thesis stage, the application of nutrients is good as compared to tailoring stage. If we look here, so in the control, the yield is less, and if we look to zinc, zinc applied in 1 splits, zinc applied in 2 splits, boron applied in 2 splits, boron applied in 2 splits in soil, and here is the combinations. Both of the nutrients, micronutrients were applied at 2.2% each. But here, both zinc and boron were applied at 2 growth stages. So, zinc and boron application in combination resulted in good yield. If we look here, so the grain yield at the boot stage was higher when the nutrients were applied at the boot stage. In the second experiment, actually I do not see the mean value because it is hidden by our I don't know why. So the second experiment is the grain yield of wheat as affected by macro and micronutrients application under water stress conditions. There was one control water spray, and phosphorus applied 1%, potassium applied at the rate of 1% full year spray, zinc applied 0.25, here boron. And if we look here, so phosphorus, potassium were applied in combination, phosphorus and zinc were applied in combination. So these nutrients were applied in a two-way combination here, phosphorus, potassium and zinc, phosphorus, potassium and boron. So if we look here to the results, so potassium plus zinc plus boron applied in combination, or both all the nutrients applied in combination resulted in higher yield as compared to the sole nutrients application. The next experiment is on maize crop. If we look here, nitrogen was applied alone, phosphorus was applied alone at 2% each. So if we look here, so nitrogen in phosphorus applied resulted in higher yield. Here, if we look here, nitrogen in phosphorus plus potash applied in combination resulted in higher yield as compared to the sole application of nitrogen, phosphorus, and potassium. And if we look to the application time, so both all the nutrients applied in 1% at 2 times, 30 days after emergence and 60 days after emergence resulted in the higher yield as compared to 2% of each nutrients at 30 or 60 days. So 2 splits application resulted in the higher yield. And if we look here, the control resulted in less yield. This is the control where only water spray was applied. And if we look, the average of the treated plots resulted in the higher yield. So this is on the maize research. Here also application of foliar nutrients increase the yield. This is the third experiment. Grain yield of maize is influenced by foliar, potassium, and zinc levels in their application time. So foliar, we applied foliar phosphorus at the rate of 1% foliar spray, 2% foliar spray, and 3% foliar spray. Here 1%, 0.5%, 0.2%, and 0.3%. So if we look here, the increase in phosphorus, foliar phosphorus resulted in the higher yield. And if we look here, so early phosphorus application, the nutrients application at boot stage resulted in the higher yield. And also the zinc, increase in zinc up to 0.3% increase the yield, but there was not too much significant difference between 0.2 and 0.3. So increase in zinc levels also increase the yield in maize. If we look to the control, there are no foliar spray, and this is the average of the all treated plots. So this means that foliar application of nutrients to maize crops under dryland condition increase the yield as compared to the control. The last experiment is the grain yield of maize is influenced by foliar potassium and zinc levels in the replication times. This is like the previous experiment. The foliar potassium at the rate of 2% resulted in the higher yield as compared to 1% or 3%. And here, in the case of potassium experiments, 0.2% of zinc was resulted in the higher yield as compared to 0.3% or 0.1%. This is again the control where when the foliar nutrients were not applied, so the yield was growth of the plants was reduced, so phenological development were reduced. We recorded data on all aspects, but here I just reported presented the mean value for the grain yield, and the rest the yield was increased when foliar nutrients were applied. This is the conclusion of the wheat experiments. Foliar treated plots had higher yield in yield components than control plots. Combined foliar application of zinc and boron increased yield in yield components as compared to sole application of zinc and boron under both water stress condition. Also, this experiment was conducted under irrigated, so it also increased yield. In the other experiment, a combined foliar application of micronutrients, zinc and boron was better than the combined application of potassium, phosphorus and potassium. Combined application of boron with phosphorus and potassium increased yield in yield components as compared to zinc plus boron and potash. So here the foliar boron application is also important in dryland condition. And combined application of potassium with micronutrients was better than combined application of phosphorus with micronutrients. And foliar application at the booting stage of wheat was more beneficial in terms of yield in yield components. These are the conclusion from the maize experiments. Foliar application of major nutrients in PK as sole or in combination improve yield in yield components of maize under water stress condition. Foliar phosphorus in zinc plots resulted in higher improved growth, high yield in yield components than control when there was no foliar nutrients applied. And the third experiment indicates that phosphorus at the rate of 3% and zinc at the rate of 0.3% foliar spray increase yield in yield components. In case of potassium experiment, when both the nutrients were applied, potassium at the rate of 2% and zinc 0.2%, so it was better in terms of economics and yield. We also concluded from these experiments that early application of phosphorus, potassium and zinc and boron at boot stage has positive impact on growth in yield as compared to late spray at sulking. So these are the some recommendation. Wheat in maize growth in yield are adversely affected under water stress condition. Foliar nutrient application not only provide nutrients to the hungry plants, but also provide water to the thirsty crops under drylands. The benefits of foliar nutrition should be therefore demonstrated to the growers in the dryland, because farmers are not practicing under dryland condition here. Crop residue in our other experiments shows that crop residue management, for example, animal manure or poultry manure management in dry land is very good. Our research, so many research indicate that poultry manure having very good response in the dry land. And our another experiment, so many experiments we conducted from the last 10 years, that biofertilizer or beneficial microbes application under stress condition is very good. It improves the growth and it also protects the crops from the adverse conditions. And moisture conservation practices, for example, mulching, and here we practice deep tillage. So deep tillage practice increases water availability. So these are the recommendations. So this means the last one, integrated foliar nutrients management and integrated crop management. For example, integrated crop management means application of biofertilizer, application of deep tillage practices, animal manures or crop residue management, along with foliar nutrients are very good for the crops under dry land conditions. These are some of the references which are published on foliar nutrition. And thank you very much.
Well, thank you very much, Dr. Amanullah. It was
Thank
again
you.
very interesting presentation. I have read many works done by workers, and on a commercial basis also the fertilizer companies have come up. Foliar nutrients, foliar applications. Calcium is also one of them. We have seen in Beijing. And now, since all the speakers have given their talks, there are certainly some queries from the participants. I think, Dr. Ritesh, shall I read out, or you will read out any question? Please,
Okay,
please go ahead.
Okay, then now Dr. Amanullah completed his lecture, and one question for him. Mr. Sri Prasad Vista from Nepal asked, Dr. Amanullah, I just wanted to know whether this experiment was conducted in rainout shelter. If not, how the rainwater was controlled in moisture stress field. Dr. Vista wants to ask this question. Can you respond, please?
We conducted these experiments at the agronomy research farm here. This is actually a water irrigation. Water is available, but we conducted these experiments in the drylands. Only water was applied for the before the sowing of the crops. The water was not applied to the crops after the sowing. So we grown these crops under water stress conditions.
Okay. So please stop sharing your screen, Dr. Amanullah. There is one query from Andre Palivoda to Dr. Yuri. Is there efficient way to manage green areas in desert even with recycled water? Dr. Yuri, please.
Yes, I'm sorry, I didn't hear the question. Can you ask it again?
Is there any efficient way to manage green areas in desert even with recycled water? Because it seems that managing green areas in desert makes more damage than good.
I'm not sure I understand the question. Sorry. Rand, did you understand the question?
Maybe I will try. So there is some positive aspects and some negative aspects in using treated wastewater. The main problem is salinity, which leads later to sodicity, okay? Which leads to low soil infiltration rate, lower hydraulic conductivity, and so on and so on. So as long as you manage salinity in a good way, as long as you monitor the SAR and so on, and if needed, you use extra water to leach the salt down, maybe you add some calcium to increase or decrease the SAR, the sodium absorption ratio in the soil. So I think it can be done. Actually, we are doing it for over 20 years, and we do see some negative impact on the soil structure. But what choice do we have? We don't have any better source of water. So what we do is trying to manage it in the best way. And I think salinity and sodicity are the main issue that the farmer should monitor and take action if it reaches to dangerous levels.
If it's okay, I will add something. This is in our condition, in Israeli water effluent condition. You need to check your water. Sometimes you have heavy metal. And in that case, you need to do some treatment or to decide to different decision. So I think the idea is to measure your water, see what you have, and after you know exactly what you have, you need to decide what to do. For example, we know that the way that we are using effluent in the heavy soil and sandy soil, it's totally different. In heavy soil, we started to see some problem after 20, 30 years, mostly in orchard. And we are trying to understand why. So I think the idea is to look on your water, and around the world you can find different solutions that you can adapt into your condition.
Thank you, both the doctors. So there is one small query from my side also to all the speakers, whosoever feels answering this. That in drylands, particularly in desert areas, now the emphasis is to improve the organic carbon. Improving organic carbon condition can further help in restoring productivity and these other things. But while we talk about the biodiversity of soils, the dry organic matter is not going to help unless there is water. I mean, how can you explain that? Dr. Amanullah,
Yes.
was I audible to people? So I said something that organic matter is being emphasized to improve the soil biodiversity and soil health as such for improving productivity. But is that helpful while we are having water stress areas in deserts and saline water conditions? I mean, good quality water is not available, water stress is there. I mean, are you getting my point?
Yes, yes.
Yeah, please.
So organic here in our soil, the organic matter is less than 1%. Organic carbon is less than 0.5%. So our research indicates that if we incorporate crop residues or we use animal manure, so it increases increasing the soil fertility. It also increasing the water holding capacity of the soils, and thereby increasing the water holding capacity of the soil increases the yield of the crops. So I think organic management in cereal, here we have cereal based system, exhaustive, we grow exhaustive crops. So organic matter management in the dry lands is very good practice. It increases the soil fertility, and if soil, it also having good impact on the soil biodiversity. Less organic matter reduce the soil biodiversity.
And of course, plant nutrient availability also
Yes,
improves.
yes, plant nutrients availability also increases.
Sulfur is recently reported to help the plants for, helping the plants for bearing the heat stress. I mean, improving the tolerance in plants for heat stress. So this session has been very interesting. Some of the very interesting presentations have been made today. And I don't see any further questions or queries coming up. So thank you guys. Anybody wants to say something? Otherwise, I'm going to close it.
I just want to reply to the sulfur. Here in my country or my area, we have the soil under dry lands or semi-arid condition are calcareous. We have calcareous soils, and the pH of our soils are very high, more than 8. So here I compared calcium ammonium nitrate, ammonium sulfates, and urea. So the ammonium sulfate is better here because of the sulfur, because sulfur decreases the soil pH and it increases the availability of phosphorus. because here the availability of zinc and phosphorus is a big problem in our soil. So those in a fertilizer having sulfur, for example, single superphosphate or potassium sulfate in ammonium sulfate, the response is very good. And if we apply gypsum or a single superphosphate here having 50% gypsum, so it increases the it having the higher sulfur in the fertilizer. So in dry land condition, calcareous soil, sulfur containing fertilizer are good strategy, I think.
Yeah, thank you so much. So I think I take leave from you now.
Thank you.
Yes.
Thanks
And,
to all of you. Thank you very much.
Thank you so much.
Yeah, thank you for all our guests from Pakistan, from India, from Israel, and from UAE. Thank you.